Welcome back, Chemistry 30. So we're in the middle of looking at some rules in terms of looking how to arrange the atoms of molecules together. So some tricks, so to speak. So looking at adding up all the valence electrons that each atom is contributing to the structure. If we're dealing with anions, and so an ion that is a negative, we need to add a couple of extra electrons. If we're dealing with cations, we have to subtract a few. And then we looked at between each atom, there'll be a bond. So we'll look at a bonding pair, and anything left over will be a bonding pair, or sorry, a non-bonding pair, which will be around the outer edges of those atoms. And I think that's where we left off. So if any electrons are left over, they're added in pairs to the central atom. These electrons are also non-bonding pairs or lone pairs. So if you have anything extra after all of that, the central atom gets more non-bonding pairs or lone pairs. These lone pairs are very important in determining the geometric structure, as we'll see near the end of MS1. When all electrons have been placed, the outer atoms will have octets, hopefully. The central atom may or may not have an octet, which is fine. So if the central atom has an octet, the structure is complete. It is all right for the atom to have fewer than 8, though, provided that the atom is boron. So boron is kind of a tricky one, because if you take a look at where it is, it's a nonmetal, but it only has 3. So the only thing it can ever do is share 3 to get 3. That'll be a total of 6. So boron could have less when it's shared, when the electrons with it are shared. And some molecules of the central atom could have more than an octet, and we'll see examples of that later. All right, so let's look at a few examples here. Then we'll look at a few scenarios at the end. So it says, construct the Lewis structure for the following. Use lines to represent bonded pairs. So the first step that we looked at was to find the valence of each valence electrons of all the atoms and add it together. So carbon, of course, we have, let's see here. So in methane, we have 1 carbon, and we have 4 hydrogens. Okay. And carbon, of course, is 4. Group 4, and hydrogen is 1. So it almost looks like we're figuring out the molar mass here, but we're not. We're figuring out the valence electrons. So 1 carbon, there's 4 valence electrons with that 1 carbon. And then with hydrogen, their valence electrons are 1. We have 4 of them. So 4 plus 4, that gives us 8 valence electrons. All right? So that's the starting point. And then go from there. We need to figure out what the central atom is. And notice that we have carbon here. Also, it's the one that appears only once. So chances are that's going to be the central atom with hydrogens surrounding it. And we can, for now, just think of it as above, below, and to the left and to the right. So then we join these up with a shared pair. And if we recalled, a single line represents 2 electrons. You can think of each one contributing electron. So if we take a look at what we have here, we have 2, 4, 6, 8. That's in fact how many electrons we have to share. So that structure is complete. Methane CH4 looks like that. Let's look at boron trifluoride. So again, I mentioned earlier that boron is a group 3. So it's going to be a little bit different. And then we have 3 fluorines. So yes, boron is group 3, so that's 3 electrons. Fluorine, of course, if you recall, it's a group 7. So it has 7 valence electrons. So we're going to have 3 electrons plus 3 times 7 is 21. So we have 24 valence electrons that we have to rearrange on the structure. So boron occurs once, so it's going to be the central atom and bonded to 3 Fs. I could go in any direction here. So far I've used up 2, 4, 6 electrons. I have 24 electrons. So when we do that, we have our bonding pairs. The remaining electrons are used to complete the octets of the outer atoms. So I place them in pairs around the outer atoms. So there we go. So this fluorine you can think of as 2, 4, 6, 8, so it's good. This fluorine here will have 2, 4, 6, 8, and this fluorine will have, it considers this to be its own 2, 4, 6, 8, so we're good. So I have 8, 8, 8. 8 times 3 is 24. I have 24 electrons. Now notice boron will only have 2, 4, 6, but that's okay because boron is an exception to the rule, as I mentioned earlier. That central atom of boron will have less because it only has 3 to share, so share 3 to get 3. All right, let's look at the last one here, PCl3. So you can see I have 1 phosphorus and 3 chlorines. Phosphorus is group 5, so it's 5 valence electrons. And Cl, of course, yes, we know that's group 7, so 7 valence electrons. So 5 plus 21 is 26 valence electrons for PCl5. So P occurs by itself. So the first step's join them up. Of course, we've only used 2, 4, 6, so obviously we need to put more around the outer elements. So just do that. So all 4 sides of the chlorines are going to be full. So 2, 4, 6, 8, this chlorine, 2, 4, 6, 8, this chlorine, 2, 4, 6, 8, this phosphorus, 2, 4, 6. Now if I look here, it's each of these sets of 8, 8, 8. 8 times 3 is 24. But look, I have 2 left over. What happens with that? So any electrons left over after the outer elements, that pair is added to the central atom. So the extra pair that's left over gets added to there. And then if we count it up, look at what phosphorus has. 2, 4, 6, 8. So everything has an octet. So that's considered to be the structure for PCl3. All right, so the last 2 examples I want to do involve multiple covalent bonds, and then we'll look at one that involves a polyatomic ion here at the bottom. So some compounds require the use of double bonds, which are represented by 2 pairs of electrons between 2 atoms. Sulfur dioxide is one such substance. So sulfur dioxide, you can see I have 1 sulfur and 2 oxygens. Okay, sulfur and oxygen are in the same group. 6 electrons. So 6, 6. So I get 6. 2 times 6 is 12. So that's a total of 18 valence electrons. So I have 1 S and 2 oxygens, so we can treat it like I'm going to have S in the middle and the 2 oxygens on the outside. 2, 4. So rearrange this. And now I have 2, 4, 6, 8, 10, 12, 14, 16. So I have 16. This oxygen's good. 2, 4, 6, 8. This oxygen's good. 2, 4, 6, 8. The sulfur, 2, 4. I'm using 16 in total, so the extra set, of course, you know, goes there. All right. So I've used up all 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. But yet sulfur, 2, 4, 6. There's a problem here, right? It needs one more set. Now what happens here is that one of the oxygens will say, okay, you know what? I'm just going to move my electrons away so that we end up sharing another set. So I have this single bond here, but this electron pair makes up another bond, so we have a double bond there. And everything else stays the same. And if you take a look, we didn't add or subtract anything. Take a look. 2, 4, 6, 8, 10, 12, 14, 16, 18. And if I look at what each item has, 2, 4, 6, 8. 2, 4, 6, 8. Then look at the sulfurs. 2, 4, 6, 8. We have an octet around every atom. Now, I could have taken from this oxygen, or I could have taken from the other one. So I could have easily have said, if I just redraw it here, I could have taken from this one and made a shared bond there. So there's two possibilities. Two possibilities. And if I look here, there are two possibilities for this particular type. And we'll discuss something later which will prove that. The two possibilities mean that this is referred to as a resonance structure. So a structure in which there is more than one possibility. More than one possibility. All right. I think we'll stop there. Then when we come back, I'll talk a little bit more about that, and then we'll look at the last example.